Good afternoon and welcome to our third lecture on computer vision. So last week we studied regions of images and segmentation. We started with discussing what segmentation is. We looked into some examples like this binarization example. We looked a little bit into Gestalt theory as well as then looked into actual segmentation approaches that are probably used more frequently. And one approach could be a histogram. We've seen some pros and cons. It's very fast, but once we add noise, it doesn't work very well anymore. We also saw k-means, which is a clustering algorithm from machine learning. And it turns out we can use it for segmentation too. And we applied this to this image compression example, which works surprisingly well. Then we said we also need more types of features, because in the first lecture we had looked at features like edges, but there are way more features such as lines, corners, and others. And we discussed initially the ransack algorithm, which is a very generic algorithm, can be used for feature detection, but doesn't work very well when there's a lot of noise. We've seen this when we looked at an example from line detection. Then we saw the Huff transform, which is an algorithm made for line detection. It can handle surprisingly much noise, and we discussed its steps and saw how it works. Then we also looked into corners, because corners are very distinctive features for objects, and we learned how we can find corners through the Harris corner detector. We described this window that moves through an image, and if the window or the movement of the window can be expressed with this formula, as we saw, and we have to simplify it. For this, we briefly revised Taylor expansion and then applied it here to the Harris corner detector, which helped us to simplify the original formula to get to this one. And then we further re-expressed this calculation and saw we can calculate this as a product of the original vector, which describes the movement of the window, with this matrix M and the vector transposed. And for M, we can calculate its eigenvalues. We also briefly revised eigenvalues and eigenvectors. And then we saw a concrete application, which is here the Harris corner detector. And with these eigenvalues, we can actually determine if there's a corner in our window or not. We looked at a few examples here as well. And we saw there are many more feature detectors such as SIFT, Hawk, difference of Gaussians, and many others. And today we will actually use these features for object recognition. And we'll see different object recognition approaches. And then, since there are some challenges when it comes to which feature detector do we use and how, maybe we can skip feature detectors and we can actually learn features on our own. And neural networks are destined for that. And so-called convolutional neural networks, they can learn features from visual data quite well. And these are the two chapters we are discussing today. And we will need this so we can have next week this introduction to the Cronus challenge. So I also want to say a few words about the next steps of this course. So next week we will have the online session as usual at 2. And Cronus, they will join at 2 and they will present this Cronus challenge. That part may not be recorded, and you're required to attend the introduction to the Cronus challenge, even if you're planning to do a different project. I want everyone to attend, and after the introduction to this challenge, you can sign up for the Cronus challenge directly after their presentation. So this will start next week, directly on Thursday at 3 p.m. after the introduction, and 2 to 3 students can join such a group. So you can join a group And I would be very happy if we fill all of these groups next week with at least 2 students. If turnout is too little and not enough students want to join the Cronus challenge, you may be randomly assigned to this challenge. I know there's the alternative of other projects, but since we have a company providing a bigger challenge, I would be also happy if we can fill these 40 groups. And we have more than 200 students taking the course, so there should be enough students. And you have 1 week to join here in iLearn. However, it's first come, first served. So once these groups are filled, you can't join any longer. And then, so you have 1 week to sign up for this. And the other projects, if in case you don't want to do the Cronus challenge or it's full, you can submit your project proposal starting Friday, April 17th. But I will say more about this in the coming lectures. So I'll say more about the projects probably in 2 weeks' time, or maybe next week already. We will see that. And then if you submit a regular project, you also have like 1 week to submit this as of Friday, April 17th for 1 week. And there'll be some more steps you need to take, but that will come, or that will be, you will learn about this in the coming weeks. So make sure you can join next week for the lecture. And today we will then now look into object recognition. We'll see some challenges around object recognition. We will see different approaches. We want to get to machine learning, classic machine learning. The next chapter would be then convolutional neural networks. And even later in this course, we would see vision transformers. But there are other approaches as well, like template matching and histograms, which are simpler approaches, but they have their own pros and cons. So the term object recognition, that's the name of this chapter. I think the term object recognition is quite a general term to describe a lot of different actual computer vision tasks when it comes to finding objects in digital images. And there was a question here why it's important to fill all the groups for Cronus. Well, we have more than 200 students, and 40 groups would be something like 80 to 120 students. They spend a lot of time on this project, preparing the data and all of that for you. So I want to make sure we also fill those 40 groups. And if we don't fill them, I would randomly assign students to the remaining groups, because the Cronus spends a lot of time and therefore also money on that challenge. And if turnout was too little, that would be quite unfair to them. So make sure you attend the introduction to the challenge next week, and then you'll see whether it's something you wish to do or not. But it will be a lot of fun, and they will also award some prizes and all of this. But they will say this next week. So that's just a short answer to what was sent here in the chat. So the term object recognition may mean a lot of different things, in fact. Sometimes there's a task, something like this, that you have an image and you just want to classify the whole image. So you don't really care about recognizing a specific object, but rather classify the whole image into a specific class. So this image here would be classified as dog. So you want to predict the type or class of some object in the image, but you would take into account the actual image, and you're not trying to find the object in here, but rather you use the whole image for the classification. That's a task that is probably the simplest task of the number of tasks we are looking now into. And you can make this more complex by looking into a localization. So a localization would mean you want to detect some object in here, and you want to put a bounding box around some object to indicate that location. But location doesn't mean necessarily that you would classify what's in that bounding box, but rather you want to find a location of some object or even multiple objects in an image through some approach, and you would put a bounding box around the object or around multiple objects if necessary. Now, you can further complicate this by saying you want an object detection. And object detection here would mean we put a bounding box around, like in localization, but next we also want to classify what's in the bounding box. And with this example here, this was first a localization, and the next step was the detection, because these objects that were found, they were also classified. So, and this one here, we see actually these bounding boxes are overlapping, which further complicates this task. And so we have actually now looked into a couple of terms like classification, localization, and detection, and each of them describe increasingly more complex tasks. Now, this is my definition, how I see these terms. Obviously, this is not the only way to define them. Some people may, for example, call this task here not detection, but object recognition in general. To me, object recognition means this is more like an umbrella term for a lot of different tasks here, but there are other definitions, and I'm fine with this. And probably I don't use these terms consistently throughout this course anyway, but it was just an attempt to define these different tasks that fall into the category of object recognition. But there are other definitions too, so bear that in mind. Now, there are lots of challenges when it comes to object recognition tasks. And there's a question here, what are some methods for localization? We'll see some methods throughout this course, especially when we see the neural networks. So I guess you would see some methods then, and we'll look into some neural networks that can do localization. But it will come later, largely in the next chapter then. And when it comes to object recognition, there are a lot of challenges. There's a lot of variation within the objects. For example, you have the same object and you may have it so exactly the same type of bottle, the same bottle, but you would have it in different images. There are viewpoint changes, illuminations can be an issue, occlusions. Occlusion means that the object is partially not visible because there's some other object in front of it, which occludes part of our object. Then also depending on your camera, you may you have the same scene and the same viewpoint and everything, but you just use a different camera and you get actually a different image out of it. For example, with some cameras and some lenses, you take a photo of a straight line and which is straight in the real world and also from your perspective, but it may not appear straight anymore in the digital image that your camera has produced. Scale can be an issue. So how far are these objects away from the camera? Are they rotated? Are they translated? So translation means in which part of the image are they? The image could be deformed as well. And then obviously you not only have, say in a class bottle, you not only have that one bottle, but you may have many bottles, many cats, many dogs, whatever. So you have a lot of variation also within the class. And then a challenge is feature extraction. We've seen different feature extraction techniques in this course already. And we've seen that their feature detectors are also affected by all of this here, by noise, by illumination, by translation, rotation. And so you will get different features in an image just based on your feature extractor. But we need these features next when we put it into some other system. Could be a rule-based system, could be a machine learning-based system. So there's also variation among the feature extractors. And also we use the same feature detector throughout the task. That one may be affected by scale, rotation, whatever. So we see object recognition is challenging. And we'll see today how object recognition works. And there are lots of different approaches in the literature. Most of object recognition that we do nowadays in modern computer vision is some sort of machine learning approach, either some more classical approach, a neural network, a vision transformer, or whatever. But there are other approaches too. And we will look into template matching in histograms. In the past, so-called statistical shape models, they were quite popular, but I think in recent years they have become less popular because we use way more machine learning. So a statistical shape model would be sort of you have a shape like in a template, but you can vary that template for based on various parameters. You could stretch it, you could compress it, whatever. But overall, machine learning is predominant nowadays, yet we still look at some of these classic techniques, at least a little bit, that you see that there is more than machine learning. And running these approaches here, they may be much faster, whatever. So oftentimes we use machine learning, but not all the time. So you should know some other approaches. Also, when it comes to maybe you work in a company and you have the task to maintain an existing system, maybe that system doesn't use a vision transformer or convolutional neural network, but some more classic approach, and you need to maintain it. That's why you should always know more than just the current fancy stuff that is available. Now, when we do so-called template matching, what we so there was a question here. I'll respond it later because we'll first see these approaches and then I'll answer the question in the chat. Now imagine we have so-called template matching. With template matching, we define the shape of the kind of object we are looking for. And what we want to calculate is a correlation. So we would go through the pixels in our image and we would see how this template would actually match with the pixels in our image. So we go through the image and so we have PQ and F of P and Q is the pixel values. So we assume here just grayscale for now. And function H is a template function. And template also has a certain size because we may want to look for some object in there. And we need to determine the best fit of the template to the image. So where the template matches the best in the image. So we move the template throughout the image. And so we want to find a point where we can maximize this correlation. That's the formula that describes this. Now let's look at an example here. Imagine this is our image and we have, so the image is this one here, the left part, and we start moving this template around and it would obviously have the biggest intersection with the first object where we get probably a perfect or near perfect match. What do you think could be the advantage of such a template-based approach? Let's start with the advantages. We start collecting either in the chat or you turn on your microphone. You can tell us what you think are the advantages of such a template approach. So now you have collected various disadvantages and advantages. So an advantage is this is relatively fast because you just move a template around. So it's super fast. The problem is, and some of you asked these questions, and obviously another advantage is it's very easy to understand, it's interpretable. Auditing could be very easy. That's all true. Um, we wouldn't need a lot of training data. Yes, we don't need that because we define the template. But the disadvantages are, what if we don't match the template? If the object is partially occluded, if it doesn't match the shape because it looks different, if the object is deformed, and all of this. Also, just scale, meaning the size of the object is varied. We also wouldn't match it. Rotations wouldn't be matched either. Translations, yes, because we would find the object if it matches the template, no matter where it is in the image. But overall, a simple approach, yet there are some use cases for it. If you have a controlled environment, maybe in a factory, and you have controlled distance, controlled illumination, maybe it would actually work quite well because it's overall super fast, so you don't need advanced hardware or GPUs, whatever. So Jensen Huang will be sad if you use template matching because he won't be able to sell you his GPUs, but that's a different topic. What do you think where we could get the second biggest match with these objects? So we have these four objects and we have a very big intersection here. What do you think sort of with which object we would get probably the second biggest intersection? So this is object one and object two, the palm is three and the last object is four. Maybe I can just do some voting here. And I also think spades, so number four, the last object is probably where we would get the second biggest intersection. We could also use a histogram approach. We've seen histograms for segmentation, and so we can also use histograms for object recognition. We could extract features from the image. We've seen feature detectors already, and there are many more. We could apply some feature detector, and we would also have stored we would then do also a lookup for each feature. And for this, we would have a hash table, and the entry in the hash table would vote for that model in a histogram. And probably the easiest thing is we can try to visualize this here. So we apply feature detection to here. So we get some sort of useful features out of here. And for our three possible classes, so the three different objects that could appear in the image, we would start looking up the features we found for this whole image. So we'll find features up here, but probably for these features, because these are very sharp objects, for these features, we wouldn't really find anything in our lookup table, because in the lookup table, we would have the features for the different objects we have, or the object candidates or the possible classes. For each of them, we would have stored possible features that a detector could find. And then we see we have some overlap with this dog. We would get some votes, very little ones with this koala, but a lot of other matches with this bear here. And we would do a voting because we have found we have matched some of the features for the dog, some for the koala, and much more for this bear. And this histogram approach, it would already help us to, for example, address rotation because this bear has been rotated. The shape somewhat looks different because the bear has also been stretched. So we find features in here, and the features we find, we have the biggest overlap with this candidate in here. We find many more features like around here or there, but they wouldn't really match with the features we have in our lookup table. So we see some advantages here because we can handle some rotation, some noise. But overall, this is still all subject to the feature detector. And probably if we have a lot of complex or if we have very complex noise in here, a lot of very varying objects, probably the histogram approach wouldn't work too well, but at least it works a little bit better than the template matching. It's also somewhat more expensive because I need a feature detector, I need to do the voting, but overall it's still much, much cheaper than some sophisticated machine learning approach. And now we'll come to machine learning. So a lot of computer vision nowadays is based on machine learning. We've seen some machine learning last week already for the segmentation. Now, with machine learning, we don't want to think anymore in terms of describing templates, matching shapes, or whatever, but we actually want to learn from examples. And there are a lot of different approaches we could use in machine learning. For example, we could use support vector machines, we could use k-nearest neighbors, and lots of other approaches for classification, for example, for now. Those approaches, however, make one big assumption. A lot of machine learning models don't work very well on raw data. If you have tabular data, they would still work okay for a lot of tabular data, but oftentimes you need to calculate features first. You can do this on tabular data, and you really have to do it in computer vision because we have two-dimensional inputs and there's a lot of noise in images. So just putting the raw image into a machine learning algorithm would lead to very poor performance. That's why things like a support vector machine, k-nearest neighbors, logistic regression, tree-based models, they would all require that we previously calculate features. But we've seen we don't really know when to pick which feature detector. It's a lot of trial and error. Plus, there are further challenges because these feature detectors are sensitive to different types of noise. So that's what computer vision looked like until some 10 or 15 years ago. And in the last 10 to 15 years, a lot has improved because we now use, in particular, deep neural networks. So neural networks have existed also for many, many decades, and they had different peaks of popularity, as we will see soon. And neural networks, they allow that they can learn features from raw data, plus they learn the task on top. So the layers in a neural network would first learn features, and then we use those self-learned features for our actual task. And there are regular neural networks, there are deep neural networks, because deep neural networks have a lot of hidden layers, and there are convolutional neural networks. They have also been available since the probably late 70s, early 80s. But these convolutional neural networks have also made a lot of progress in the last 10 to 15 years because of this deep learning movement and all the advances that have been made since then. And that's why we will now come very quickly to convolutional neural networks because they are a very helpful approach for the problem of object recognition. Every year, a lot of students pick some neural network approach for their projects. In recent years, transformers have made more progress, but there are also some type of neural network. They make some other assumptions. We'll look into them in selected topics, but we'll start with the convolutional neural networks today. Who of you feels comfortable with neural networks, meaning you have implemented some neural networks, you know some of the theory? If you've done this, send your thumbs up. If you don't feel comfortable with neural networks, send thumbs down. And there are some students that feel okay, but many don't. And that's no problem because this course is supposed to be in the fourth semester of your AI bachelor's. And in parallel to the computer vision course, you have the machine learning course. So you've also just started a few weeks ago, the machine learning course. There's also a deep learning course in 1 year from now, in which you would learn even ever more about deep learning and neural networks. So today in this course, we'll actually start with neural networks. There'll be a bit of an introduction to how they work, how we can train them using backpropagation. We have loss functions. And some of that will certainly overlap with things you would see in your machine learning course for the remainder of your semester. And once we have established this, well, I think the machine learning course doesn't address neural networks too much. That's why we have this deep learning course later in your studies. But the things we discuss and the methods we discuss to train neural networks, this is something you will definitely see again in your machine learning course, in the deep learning course, whatever. And then this is a light introduction, or maybe not that light, depending on how you see it, to neural networks. And then we will fully focus on convolutional neural networks, which are an approach that is particularly helpful for images, plus some other types of data. And we'll see how we can train them. We can see how we can optimize the hyperparameters of a neural network. And we see some approaches of how we can train a neural network efficiently. And since you don't need to reinvent the wheel, there have been various selected architectures of convolutional neural networks, and we'll discuss them as well. And some of that could be reused by you when you build your own vision system. So this is the agenda for today. And you remember the term convolution or mask or filter or kernel or whatever from 2 weeks ago, where we said we have this convolution or kernel and we move this through an image to calculate a new image. And we've seen if this is our image, we have, for example, which are pixels A, B, C, D, and so forth up to KL. And we have this kernel here, and we apply it to the upper left of this image. We would multiply the value in A with X, B, A and W, so A and W, then B and X, E and Y, and F and Z. So we would have 4 products and we sum them together to get to a new pixel value in our image. We would then move the kernel to this section here and so forth. And eventually we compute a new image. This here is depicted now simply for grayscale images. So all of these, so each sum of products would lead to a new grayscale value. That's what we, and there could be some normalization, obviously, in this kind of stuff. You've seen this. And now our goal today is to look into convolutional neural networks that are inspired by this approach. First of all, we need neural networks. And some of you said they have used neural networks already or they feel comfortable. Maybe for those of you who have used neural networks, you can send us a little bit in the chat or turn on your mic what you have done with neural networks, what kind of problems you have applied to, maybe how much you have learned about how they work. And just keep sending this in parallel while I'll provide you here with the introduction to neural networks. And then we'll collect, because I'm just curious about how much work some of you have done. If you have never done neural networks, no problem, because that's why you're here in this class. And we'll make it all the way to convolutional neural networks today. Now, a neural network has a so-called input layer. So we have layers, which is a column in here. We have an input layer and we have an output layer. And we can feed in a certain number of values per input, concretely d many. So we would have d many input units, one for the first value, then for the second value, third value, and so forth, up to the dth value. Imagine I have I have one sample that has 100 entries and I would need 100 input units. We'll come to images later. For now, we just assume it's some type of data. And I can use a neural network for lots of different tasks. For example, I can use a neural network for classification. So I would have k many output units. And my goal is I put in an input, and finally I do a so-called forward propagation. That means I go and take the input and I forward propagate it towards the output of the neural net. We'll see in a moment how this can be done. And eventually we'll have an output value per unit here. And now we wonder which class is it? We would take the output unit with the largest value. And then we would have classified the input. Why is this called a neural network? Because this, eventually it's a graph, but these nodes we got in here, that's what we call a neuron. Very importantly, neural networks do not work like the human brain, not anywhere close, but maybe these neural networks are very loosely inspired by how the human brain works at the very most, but it's much simpler. Now, what we got between the input and the output layer is at least one hidden layer, possibly even multiple hidden layers, and we interconnect the units in some way. The simplest type of connections that we got is, or the simplest connectivity we've got is, we would take the first unit in the input layer and we would interconnect it with all layers with all units in the hidden layer. So this unit gets connected with every unit in the hidden layer. Then the second input unit would also get connected with every unit in the hidden layer, and so forth. So every unit in the input layer would get connected with every unit in the hidden layer. And then every unit in the hidden layer would get connected with every unit in the output layer. We could have multiple hidden layers. So then again, every unit in the hidden layer is connected with every unit in the following hidden layer. This will lead very quickly to lots of connections. Imagine we have a hidden layer with 1,000 units. And in the next hidden layer, we also got 1,000 units. That means we already got 1,000,000 connections. That's why when you build your neural networks, they very quickly have millions or even tens or hundreds of millions of connections, possibly even into the billions if you build a very large one. And we'll see different architectures later today. And we also have these other units here, as you can see, X0 or Z0. These are just the bias weights that we would also include, but you'll see the formula of how such a neural network works in a moment. Now, that's the idea of neural networks, and these connections, they are a numeric value. So there's a certain numeric value for this connection, say from X1 to Z1. There's a different value from X1 to Zm. And the training would mean that we set these numeric values, they are parameters or weights of the model, in a way that the neural network can predict the corresponding class for an input. We can do other stuff with neural networks too. It's not just classification. We could also use regressions, or we could have one regression unit. For example, we want to calculate, for example, the size of something or the weight of something or the value of something. So we would put in an input and we would regress and calculate an output. So not a classification, but a regression. For a regression, we could have, for example, just one output unit and there will be some continuous value coming out of there. We can use neural networks for clustering, so also for unsupervised tasks. We can use neural networks to even generate new images, because what we get out here at the end could be not just classes. We could have also a certain number of pixels in the output. So we would generate like a new image. So this architecture is very, very flexible. And there are lots of other ways I can connect these units. I can even use neural networks for working on time series and lots of other stuff. So there are lots of variations of this type of architecture. You would learn in detail how neural networks work, for example, in your deep learning class. But today is meant as an introduction to the key features of neural networks. Plus, we will see how this can be used eventually for computer vision. Meanwhile, some of you have sent some comments that one student says that his view on neural networks is like there are a lot of simple models working together, and so you have a small part of a task, and eventually you would combine all of them. That's actually a good part, and I'll say more about this later. And there are also some comments that neural networks are so-called black box models. I'll come to this in a moment as well. Now, these neural networks, they are very, very helpful because they allow us to learn very complex hypotheses, so very complex patterns from data. And they are mainly used for discriminative tasks like classification or regression. They can be used for generative tasks as well. They can be combined even with reinforcement learning, so deep reinforcement learning. They can be used for unsupervised tasks like clustering, whatever, or for dimensionality reduction. But we'll focus on this course mainly on classification for now. We'll see generative approaches towards the end of the course when we look at transformers or generative adversarial networks. But we'll focus today, I think, largely on classification, plus some other object recognition tasks like localization and so forth. Neural networks are actually nothing new. Neural networks go back to the 19 or to the 50s, actually, in which early neural networks became popular. Sometimes there are even some claims from even before the 50s. But I found this plot here some quite a while back, like in 2014, that actually visualized how or what the history of neural networks looked like. And early neural networks were actually nothing like a network, but it were simple units. Someone said a neural network now is a combination of many simple models working together. In the early days, they were actually just one simple model. And this very simple model here was called a perceptron. A perceptron is in fact a very simple linear classifier that you would have inputs for, and for each input you have a corresponding parameter or weight in a model, and eventually you calculate an output. These perceptrons, they are very simple, yet they are also quite limited. But later in the 80s, 70s, and 80s, people noticed one can combine these perceptrons. And nowadays, an interpretation could be that every unit in here in the neural network is sort of a perceptron. That's why sometimes people say a neural network is a multi-layer perceptron. So an MLP, I've just sent a word to the chat, MLP, for a multi-layer perceptron. So we have multiple units and multiple layers. So we stack a lot of perceptrons together, in fact. This is not fully true actually. We don't really use perceptrons anymore, but we use logistic regression units, which are also classifiers that you would learn in the machine learning course. But they are much better to train than a perceptron because they actually have an error function that we would optimize, while training a perceptron is quite a difficult adventure and an unreliable adventure, in fact. But we'll see this difference later. And then the initial perceptrons, they were not that powerful because they were just linear classifiers, but it was noted in the 70s and 80s, if you combine a lot of them, you can actually calculate very complex nonlinear hypotheses. And this is something that became super popular in the 80s. And things like handwriting recognition, autonomous driving, some of these approaches, at least early ones, have already existed in the 80s and 90s. But then there was a so-called AI winter, and this AI winter, in fact, this was the second AI winter in the history of AI, led to a loss of popularity of not only AI, but also neural networks, so neural networks and AI as a whole. because it was noticed that these neural networks, they have some downsides. For example, the bigger you build the neural networks, the more data you need. Otherwise, they would overfit. Overfitting means that you learn a pattern very, very well, but you're unable to generalize to new input. So you learn the patterns from your training data very well, but this is where you get stuck and you're unable to generalize to unseen examples. That's overfitting, and neural networks are very prone to overfitting. You could address this with more data, but more data means more computing power was needed, and that was limited in the 90s and early 2000s. And there was this loss of popularity. And then around 2006, something happened. A very influential paper was presented and that were published in that time that proposed new training methods for neural networks that could address the overfitting to some extent by doing so-called pre-training of a neural network before the actual training. And this appeared, yeah, some 20 years ago. And then in the following years, industry became aware of this, started to adopt it. And a lot of new works then appeared on neural networks. And this actually allowed to also build deep neural networks. So neural networks that have a lot of hidden layers that can learn features very, very well. This was already understood in the 80s and 90s that that could be done, but there was a lack of data, lack of computing time, lack of algorithms that could do this well. And this became slowly available then after 2006 because more people started publishing new algorithms, more data was available, computing time became cheaper. And then when this figure here was published 12 years ago in a journal paper, which was a survey paper of deep learning methods at the time, there was the question how all of this would evolve. And what we've seen nowadays is that this has really gone through the roof since 2014 because ever more people keep working on neural networks, keep publishing works. We have better hardware, we have more data. We now have transformer models. We have very sophisticated generative AI models that are based on transformers and other approaches as well. And all of this has really gone through the roof because in this hype curve in 2014, it was sort of uncertain where this would go, if it would plateau, if it would drop, if it would really go through the roof. And it went massively through the roof. And we now all use lots of deep learning applications. So this is a bit about the history of neural networks. And now, how does a neural network work? I think for this, I will switch to my iPad, and I'll show you some of the math, how you can actually do calculations in a neural network. So we have looked into a simple neural network, so neural networks. And we have an input layer. So input, we have a hidden layer and an output layer. And obviously this, what I'm showing you now works for many more layers. And we have input units. We have hidden units, and we have output units. And the number of them may be varying. And then we have these connections here. So we connect the first input unit with all the hidden units. We connect the other input units also with them. And then we keep continuing with these connections so that we have connections between the units in the hidden layer and the output layer and so forth. Now, we'll come to the training and finding how we can connect these units or how we can set the parameter values. That's what we will see in a moment. But the first thing we want to do is a so-called forward propagation. So for now, forward backpropagation. For now, we just want to see, assuming the neural network is trained, that all of these connections, so the parameters or weights in a model have been set already. How can I actually do a forward propagation, meaning I put in something and I want to get my output. So I have numeric values in the input units, and imagine I want to calculate now the value of this unit. How can I calculate it? So I have a value Z for now, and Z will be computed as a sum of products. What I have is, say, the input was called X1 up to XD in my slides. And this one here is Z1. And I want to calculate the value of Z1. So what I would do is I take the value of X1 and I multiply it with a corresponding weight. And the weight I have is this one here, connecting my unit X and my unit X1 with my unit Z1. So this would be a weight. And for example, this weight could be called weight, say, for example, 1, 1, because it connects X1 and Z1. So I would multiply the value of X1 with the weight 1, 1. Then I have my next unit, which is X2. I would take and they are also connected because X2 is also connected with Z1. So I would take the value of X2 and I would multiply it with the corresponding weight value. And this weight could be, for example, called, but that depends a lot on the literature, what you would call this weight. It could be, for example, called weight 2, 1, because we take X2 and connect it to Z1. So here it's called weight 2, 1. Sometimes in other literature, it's called weight 1, 2, because we map from 2 to 1. So this depends a lot on the literature, how you put the indexes. But here we just call it now weight 2, 1. And we would continue this for all the input units up to our XD. And XD is also connected to Z1. So we would call this weight D1. And we multiply the value XD with the weight of D1. Are you all okay with up to here for this? Maybe just confirm thumbs up, thumbs down. So I calculate this sum of products. And then I have calculated the value of Z1. I would do exactly the same for Z2 up to, before we call this one here ZM. I would keep doing this up to ZM. And I would have calculated Z1, Z2, Zm. And for Zm, so this one here, I would obviously take the connections from X1 to Zm, X2 to Zm, Xd to Zm, and so forth. So there are different connections here. I would again have a sum of products, and then I would have calculated all the values in the hidden layer, and I would keep doing the same now for the output layer. For the output layer, I would have this called like Y1 up to YK. And in order to calculate the sum of products, I would take the value of Z1 times the corresponding weight up to the weight of, or the value of Zm times this corresponding weight. So I would have a new sum of products, and I would do again this for all the output units, where I would always calculate a sum of products. And this is a forward propagation. And eventually I would have calculated the values in my output layer, and then I would take the output unit with the largest value. That would be the class that I have picked. For example, if this is, say, in Y3, then whatever Y3 stands for, that class would be the result. For example, if we have handwriting recognition where we have characters A through Z, we would have, for example, 26 output units. We just assume like uppercase characters, no digits. We would have 26 output units. And what we would feed in could be an image. So the input image could be, for example, a 100 times 100 input image. So we would have a pixel image in here, and we would have something like this. And this pixel image would then be classified, for example, as an A. An A could be my Y1, or if it was a C, it would be the Y3. How do I feed such an input image in here, say with this classic neural network architecture? This classic neural network architecture expects a vector. So what I would do is I would build a vector from the 2D image. So the vector would be just composed of, it would be one long vector, just cluing all of these rows together. So the input vector would be 10,000 pixels, and I would just clue all the rows together to get to one long vector. We'll later see if this works well or not for images, but we'll see that. And then I would feed it in here, and through my forward propagation, I would classify it. And I have assumed so far that for this here, the weights would already be set well, so the classification would work. Maybe just confirm that you're okay up to here with how such a forward propagation would work. Good, seems fine. Now, one thing we would typically do is we would not just take these Z values, but rather, there's a question here. So each of the 10,000 pixels are mapped to the neurons. Yes, we would have one input neuron for each pixel. So we would have 10,000 input units, and we would have 26 output units, and maybe we would have like 1,000 or 5,000 hidden units. We will need more hidden units, so more hidden layers, that this actually works well in practice. So in practice, you would oftentimes have more hidden layers, but we'll see that later when it comes to deep learning. But I hope that addressed the question. Then there's one more thing. Also, if you look in the slides, there were these bluish dots. So there were these dots here. There was this X0, there was this Z0 also. Now you wonder, what do they mean? These are the biases. A bias means that I not just have the sum of products, but I would actually add something on top of the sum. So I would add on top my X0, and the X0 would be always added on top for the hidden layer. So also for my Z2, I would have the X0 here at the end and up to Zm. So this would always be added on top. And such biases are common in machine learning models. As you know, in a linear function, we also add the y-intercept on top, and this is called a bias weight, which we add on top. It also needs to be learned, but it just helps us to shift the learned pattern around, that it doesn't start in the center, but we can actually move it around. So it's like the y-intercept in a function. But this bias weight is something quite common in a lot of machine learning models, so you have probably seen it before. But this one here was also depicted in the slides. That's why I've mentioned it briefly. Now the slides show one more thing. We typically don't use these Z values directly, but we would still transform these Z values into something. So our Z1, our new Z1 would take the old Z1 value and we would still apply it to a transformation function. So chi is a transformation because these set values, they make it very, very big. So if this is a big neural network and these weights and so the weights can be positive or negative. Still, if you build a large sum of these products, you could have a very large positive or a very large negative value. And if you train a neural network like this, it's not going to work very well. So we want to keep these set values in a certain range. And for this, we use such a transformation, which we call often an activation function. And in classic neural networks, a very common activation function is the so-called sigmoid function. The sigmoid function looks something like this, sigma of x, and this would be turned into 1 divided by 1 plus e to the minus x. Have you ever seen such a function before? The sigmoid function, maybe thumbs up or thumbs down. We can also try to visualize this sigmoid function, and some of you have seen it. So the sigmoid function can be visualized. So we have x here, and x would be now a value, and the y value will be here between 0 and 1. And if we try to visualize the sigmoid function, it would look something like this. So for large x values, it converges or it goes towards 1. For very large negative values, it goes towards 0. And for x equals 0, we would get 0.5. So this is the sigmoid function. We are still now with classic neural networks. Later, when we come to deep convolutional neural networks, there are other activation functions available. But these activation functions, they help us that these Z values stay between 0 and 1, so the neural network becomes more trainable. And we would use this for the hidden layer, for the output layer. So we would feed in the input values as they were, but then we apply this activation function for the Z values in the hidden layer as well as for the output layer. Unless I want to do regression in the output. So far we said we want to do classification with the output. If I do regression with the output value, I don't use an activation function in the output layer, but I would still use it in the hidden layers. Because when I do a regression, I don't want the value to be bounded but between 0 and 1. But for now, we anyway largely focus on classification. Now, this is a forward propagation in the neural network. And we have assumed that these weights have a specific value that was set already. We will now see how to find these values, so how to train the neural network actually. And for this, we'll go back to the slides. What I have just shown you is the forward propagation. This is also shown here in the slides, just with a couple of more indexes to identify all the objects properly, or the Z values if we have multiple hidden layers. But for now, that doesn't matter. So I've just simplified it a bit in the slide deck and left out some of the indexes because we wrote out the sum of products. We've seen the sigmoid function. Now I need to calculate a so-called loss function because our goal is we want to determine now how good or how bad is our neural network for our task. And in our task, we got labeled inputs. So we have our inputs, could be images, could be some other vector inputs, but they always have a label in classification. So we know for the training data to which class they belong. If it's a regression problem, we also know the regression value. And we want to now learn a function that maps from the input to an output. Always with the goal of generalizing. So when we have new inputs, we want to find an adequate output. Could be a classification, could be a regression. And we also, when we train the neural network, we need to determine the weight values or the parameter values. And for that, I need to know how good or how bad so far my neural network is. And for this, we use so-called loss functions. Sometimes they are also called cost functions or error functions. Oftentimes these terms, they mean pretty much the same. And what we need is a function with which we can quantify how good or how bad our neural network is. And I'll tell you a little bit about my notation, how I write down these things. If you talk to other people, they may give you different terminology, but I try to use my terminology consistently throughout this course. Last week, I told you when we looked at clustering, M always means the number of examples. To me, not N. N like Nigeria. This means to me how long the input would be. So how long the vector would be. But M means to me the number of examples. And for these examples, I use X, which in bold because it's a vector typically or some other structure. And this has index I, so an upper index, a superscript. We've used this notation last week for clustering. And for my example X, I have the corresponding label. The label is just a scalar value, could be a class, could be a continuous value, and I have a corresponding label for my corresponding or for my example. Maybe just confirm that you understood the terminology up to here, what M means, what the example means, what the index means, and any questions, please ping me anytime. If you look into other literature, they may define this differently. And this is sometimes a pain when you start learning, you read lots of different literature and everyone uses different notation. So I at least try to use my notation here throughout the course consistently as far as possible. Now, I also have the so-called hypothesis age. And the hypothesis in this case is just the machine learning model, like the neural network. And I put my data, my example into the neural network. It will predict something. It will predict the label. And I know the ground truth. So the label for we just look at training examples for now. I know the correct label for my training example. And the neural network will predict something, and the neural network could predict exactly the label value, then this difference would be zero, but the neural network could predict something different class, different regression value. So there would be a difference. And that difference can be positive or negative, but we don't want to add up positive and negative values. That doesn't lead to anything. So we only want absolute values. So value 0 or positive, we could calculate the absolute value, but what is quite common is we square these errors. So small differences have very little impact, big differences have big impact. And we do this for all the M examples where I make a prediction, I calculate, or I predict the label, I know the ground truth, and there's a difference, square the difference, and sum them up. This could potentially, say, if I have millions of examples, lead to quite a big sum. So something that's quite common is we divide this cost value or error value just by M, just to normalize it based on the number of examples, so it doesn't get just out of control. The last thing here is the theta. Theta just means the parameters. Um, Sometimes the notation refers to theta for the parameters. Sometimes it's a W for a weight. In this regard, my course is probably not 100% consistent, but the literature is also not. And here, the hypothesis, the model just means the model with the set of parameters or the vector of parameters. And for these parameters and my examples, I want to calculate an error. We'll see in a moment what it's useful for. This squared error is quite a common error in a lot of machine learning tasks and also in a lot of other statistical problems. This one can be used for classification. It can be used for regression. In practice, when you do classification, you don't want to use this squared error too much for you would use it for regression, but for classification, you typically don't want to use it. There's a better sophisticated cost function. It's called a cross entropy, taking some information theory into account. I will not explain this now step by step. But when you build your neural networks, you would anyway use a library. We'll see some libraries later to reuse work of others. And there you can pick the cost function. And for classification, you would typically pick the so-called cross entropy cost function, which has various benefits. But this is something you would learn in detail in a statistics or in a machine learning course in case you have not seen it before. Now, we can calculate errors now, and now we want to use these errors to optimize the weights in the neural networks. Um, this is something I will also show you again on the iPad. We want to optimize the parameters. So parameter optimization, which are these weights we have seen here before. And I want to optimize them because initially when I start in a neural network, for a learning task, I don't know the value. We could assume initially they're all random values, they're all zero. Then my predictions don't make much sense, so I need to determine the weight values in order to train the model, and then it will make better predictions. Now assume we have a very simple statistical model, not a complex neural network yet with a lot of weights, because I told you before, we easily have millions of weights. Just we have one layer with 1,000 units, next layer with 1,000 units. We have a million connections. So we have here this error or cost. So E for error, C for cost. Sometimes J is used in optimization to describe the loss function. And so these are all synonyms. And imagine I only have one weight for now. So we could use a weight or alternatively a theta just for a single parameter here. And when I start with some initial value in my model, the initial value could be zero for the weight, could be a random value. Um, I will have, say, my weight, and we call it weight, just, well, let's call it initial weight. So we call it weight initially. And up here, I will have some certain error. We assume now the cost function is relatively simple. We could assume initially that our error function or cost function would look something like this. In reality, it will be more complex, but we'll see this. So I'm starting with my initial weight, and I have this error up here. And I want to get to down here, which is the minimum. So sort of the optimal weight. The arrow may not be zero, but at least there's a minimum. And we assume in this error function here that it's convex, so there's only one minimum here, which is the global minimum. So I want to get to down here. That means I need to change my weight value in order to get to the goal. So the goal is down here. It's sort of the weight. Well, I'll write it here. So weight star could be the optimal value. I need to go and there's a question how we determine the weight. The initial weight could be just zero, could be a random value. In a lot of machine learning models, the initial values are all just zero. In a neural network, we would often just choose random values, small random values around zero. We'll see later why, but for now, you could just see this as zero or some small random value, could be positive or negative. And typically, we would also aim that in machine learning models, the weight values are all relatively small, either positive or negative, around zero. We often avoid very, very large positive or very, very large negative weight values because this creates a lot of disturbance in the models. Sometimes you would want that, but probably quite rarely. So we always would anyway aim for small weights. But that's kind of stuff you will see in detail in a machine learning course. You know, when I started as a professor, I was really hoping I could teach the machine learning course, but it had in the AI bachelor's. We had this German language AI bachelor's at that time when I started 6 years ago, because it was founded 6.5 years ago. So the machine learning course was already assigned to one of my colleagues, concretely Robert Hable in the German language program. So I was sort of sad in the first moment because I couldn't teach machine learning. But then the computer vision course was free or not assigned yet. And then I was happy instantly the next moment because computer vision is based a lot on machine learning. And that's why what I'm saying here is probably a lot of details today, also about machine learning. Not all of that could be clear at the very beginning, but as you progress with your machine learning course, maybe come back to this class that we are recording today to see some of these concepts again. Then, and we have Professor Meyer who teaches machine learning in the English language program. That program was founded later, but then I was already teaching enough courses. And when this machine learning course came up then, or that course came up then, Professor Meyer got it. So I never got the machine learning course in the department, but that's fine because we do lots of machine learning here in this course anyway. And now I only have one weight in this very simple model. How do I get this minimum? So how do I find the weight value to get to the minimum, to get down here with classic math? Not any sophisticated math, but with what you learned in high school. Maybe tell me in the chat quickly how I can get to this minimum. One person wrote something that we should go into the direction of the local minimum. Yeah, but how do I do this? Nothing super advanced yet. It's just a single parameter. So tell us, yes, we would need the first order derivative. So if we have this arrow function, I would need its first order derivative, and where I have so the change, and I don't have change in a minimum or maximum. And here there would only be one minimum, there would be no maximum, no other minima. So that's why with the derivative, where the derivative is zero, I'm in the minimum. So I could do an analytical solution from the squared error function or the cross entropy, and I could solve this analytically and get the exact solution, hopefully. But for the squared error would be doable. However, this becomes now, unfortunately, more complex. We need to go far beyond high school math because in the real world, our machine learning model not only has one parameter, but millions or billions. I could solve this analytically for two parameters. There's some math I could do, but not for millions. So I need a numerical solution or a numerical approach. I will not find the perfect weight, but I will try to approximate it. So what I could try is I could go in towards the minimum. This is what was proposed. Now, when I'm starting here with my so the derivative will go in this direction because the function is growing. That means I need to go into the opposite direction, the opposite of the derivative. So I need to go somewhat in this direction. Then I have a new weight value. So weight new, or we call it weight prime, for example. There, I again have a positive change. That's why I need to go again into its opposite direction. Well, trying to highlight this better to here. And I would keep doing this repeatedly until I converge, until the next iteration where I only have a very, very small change in my weight value. So it's a numerical solution. And I have to do this because I now have a lot of parameters, not just one. Maybe just confirm that you're okay with this up to here, that I go into the opposite direction of the change to go to the minimum. This would also work. The math we see would also work if we started over here, because we then have the change down here, but the approach we'll be seeing works either if you start on the left or right of the arrow, just to say, because we'll introduce the math now momentarily. So down here is the goal. This would be our minimum. And in fact, here it's a global minimum. And what do we need to do in order to express this in terms of math? And I'll show you this now. Imagine, again, we only have one parameter for now. So I'm writing some pseudocode for you. So until convergence, I need to do the following. Say I take my weight and I update the weight value by taking the weight value as before and I subtracted that change. Because I said I need to go into the opposite direction of the change. So I need to subtract the change. That means I take my weight value and I subtract the change, and the change could be just written like now, like the error function, how it's changing. So I subtract that. You'll see a better formatted version in the slides in a moment. And I would do this until convergence, so until weight only changes very, very little, because initially it will change a lot, then it will change less, and you see these steps, they keep getting smaller and smaller. Now I can update this with a couple of further points. I not only have one weight, but I have multiple weights. So I have a weight 1. So I need to express this change of the error function along my one variable. Before I wrote this E prime described the change of the error. that one could have also been written when before we only had the weight, as well, we just assume we're still now at one weight. I could write this, the change of E along my weight, where I only had this one variable. But now we'll make it more complex because I will have multiple weights, but I cannot write it like this in math. I cannot use this D, but I need partial derivatives to express this. So the partial derivative of E along my weight 1. There's a question here about the Newton method. The Newton method can be used or bisection. Well, the Newton method describes something slightly different. So the Newton method can be used to find the root of a function. So where the function is 0, you can amend the Newton method also to find the minimum in a function. So classic Newton method you would use for finding the roots, the zeros of the function, which we don't want here. We want the minimum, but you can amend the Newton method. And the Newton method is in fact also one of many possible optimization techniques in a neural network. I'll come to this in a moment, but thanks for raising this. So this is a partial derivative. Do you all feel comfortable with partial derivatives? Maybe thumbs up or thumbs down if you feel comfortable with partial derivatives. And maybe some more responses, please. Okay, so everyone feels comfortable because this was also taught in your first semester. Now, I not only do this for one weight, but for multiple weights. So for up to weight, we can say weight K, for example. So, and I take the value and I subtract the change, because remember here, I subtracted the change to go in this opposite direction. And I would do this for all the weights. So I take the error function and I take the partial derivative along my kth weight. There are a few things that I can still tweak here. And k may be quite large. Maybe I have millions of parameters. And since I subtracted the change, remember I told you what happened if we started over here on the left of the minimum. And here the change is negative, but if I subtract a negative change, so minus minus would be positive. So this would also allow me to go towards the minimum. So minus the change works from either side, just to highlight this. And this algorithm here it is called gradient descent. What I have implemented here, gradient descent. It's a numerical algorithm, an optimization algorithm that tries to find the minimum in for such an error function and tries to update the weights to get into the minimum or approximate the minimum. Are you all familiar with the term gradient? Maybe thumbs up, thumbs down if you remember what the gradient is. And those who remember it, maybe you can just send us to the chat a quick definition of what gradient actually means. And one says slope of a graph. Yeah, but that's also the derivative, say um, along one variable. I'll wait and see if there are more responses. And the gradient, so I just put an excursus here, the gradient, oh, I'll write this better, just wait. The gradient is a following. Imagine I have a function of x1 and x2, and it's something like 2x1 squared plus 4x2. We'll do the partial derivatives. So what's the partial derivative of f along x1? You can send me this to the chat. And the partial derivative of f along x2. And then we'll also see if you remember partial derivatives. And the function is 2x1 squared plus 4x2. And when you do partial derivatives, you would do the derivative along your variable, and all the other variables would be considered just constants. So the partial derivative along x1 is, so it only addresses this part here. So it's 4 times x1. And here for the x2, we ignore the other part as well. So it's just 4 and the x2 disappears. Now the gradient of a function, gradient is often written as such a nabla. Gradient of f is a vector of these partial derivatives. So the first entry would be the first partial derivative, and the next entry would be the next partial derivative. So the gradient of f would be 4x1 and 4. Does that ring a bell that the gradient is the vector of partial derivatives? Maybe just send a sign. Good. Now we can wonder why this algorithm is gradient descent. Because what I have here is a partial derivative. Here I have a partial derivative. So in fact, this algorithm could be rewritten, and we could also say that I have my weight 1, I have my next weight. Finally, I have all these weights in a vector, and I have all the partial derivatives in a vector. That's why this gradient descent could also be written. I have my vector weight, or my weight vector, so a vector, where I take the weights and I subtract the partial derivatives, and and what I need is a vector. So this here is the gradient, and I update my weight vector by taking the values and subtracting the corresponding partial derivative. So rather than writing all of these statements, I just have one statement now where I have a weight vector and I subtract a weight vector, which is, or I subtract a vector, which is the gradient. So gradient descent can be written in 2 lines, for which I need the loop until convergence in the vectorized statement. Maybe just confirm that you understood this. Seems okay. There's one extra thing I can do in here. Something that can happen in neural networks is, and we've seen, we want to make these steps here and they get smaller. But maybe initially these steps here are too small. Maybe means I only do a very small step, then another small step, and keep making very small steps. And there was a question here, when does it stop? Well, still until convergence, when overall the weight vector doesn't change much anymore. So when all its elements only make tiny changes. So I would need to define a threshold, and then it stops, because I've just replaced these lines in the gradient descent with one vector equation, or one vector formula. But it could happen that these steps initially are too small. It could happen that these steps are too big. So it could sort of happen that it overshoots because these steps are too big, and then I also don't reach convergence. Who of you knows what I need to do now? Some of you have said they have done machine learning or neural networks before. What is it that I need to do in order to make sure that these steps are not too small and not too big when I aim for convergence? If anyone knows it, send a thumbs up, because some of you said they have done neural networks before. If you don't know how to control the scale of these steps, maybe send a thumbs down. If they're only thumbs down, I'll reveal it. So what I need to do in the gradient descent is I need to multiply these partial derivatives with a factor. And this factor is alpha. It's the learning rate. So the learning rate is a factor by which I multiply this partial derivative. That's now what someone wrote. And this learning rate is typically a small value, maybe 0.0 something. It's not a big value usually, but this is one you need to determine experimentally. And the learning rate is a so-called hyperparameter. Hyperparameter. So we have parameters in a model. The parameters are the weights, but the hyperparameters are extra parameters of the overall model setting. So hyperparameters could be the learning rate. A hyperparameter could also be the number of hidden units, the number of hidden layers, and other things. We'll see more hyperparameters later. And all of those hyperparameters, they need to be tweaked too when you train your machine learning model. So you would train it, you would train the model for a certain set of hyperparameters, and then maybe you see, the outcome weights are not very good. So I change, for example, the learning rate, and then I retrain the model. So I also need to optimize hyperparameters. That's what you need to bear in mind. And there are some questions. Are there automatic ways? Yes, there are many ways. We'll see this later when we progress with efficient training of neural networks. Then, last point, we had this very simple function here. So this was our error function. In reality, when you have a complex neural network, your error function will not be convex. Convex means just one minimum, but your error function could look totally different. It could look, for example, like this, where you have multiple minima, and the risk is that you would get stuck in a local minimum, like up here, and you would not make it to your global minimum. That's the reality when you train neural networks, especially complex, deep neural networks. You will never really make it to the global minimum, but you aim to get to a good local minimum. And there are lots of methods that help you with that. It's not guaranteed, but there are a lot of approaches, at least helping you to find an okay local minimum rather than finding a really, really bad local minimum. You will not really make it to the exact global minimum, though. But that's the reality. So in reality, these error functions look far more complex. Then, and most what I'm showing you here today is can be generalized to a lot of other machine learning models, so not just neural networks. So this is something you would see again in your machine learning course and the neural network stuff again in your deep learning course. So the gradient descent that I had shown you, here it's written slightly differently, that I repeat this until convergence. And what I write here is not a weight, but a theta sign. It's also a weight. And I'm updating my weight by taking the weight value, and this is just an assignment, and I subtract the partial derivative of j. Here it's highlighted j for these thetas, so for all the weights that I got, and I take this partial derivative. And I'm doing this for all the j's, so I'm not just writing, before I wrote out the first weight, then the second, up to the kth. Here it's just an index. But this is just essentially the same as we did before. It's just a slightly different notation. And what you recognize here is the learning rate alpha. This Gradient descent is sometimes also called batch gradient descent. Batch gradient descent means you take all the training examples where you have m many. The problem is an update. So one update in this loop can be super, super slow because imagine you're not just, you need to calculate these errors in here. For example, you need to calculate the error, and I've shown you how to calculate the errors, for example, through squared errors or cross entropy or other ones. But if you have millions of examples, calculating this error can be quite slow. And then you're just doing one update in this loop, and this loop may run a super long time. And if each update in the loop is slow, reaching convergence can be super slow for a lot of examples. Especially maybe imagine you have a lot of examples, too many, so they even don't fit in your RAM, and you need to load them from disk. So you need to load the first million examples, then the next million examples, then again. And then you always do swapping. That means it's actually super, super slow just to calculate one update in here. And you need to calculate a lot of updates, and you have a lot of iterations of your loop. So this becomes super, super slow, at least when you have big data. And so we don't use batch gradient descent in practice, but we use something that we call stochastic gradient descent. Stochastic gradient descent is slightly more complex than our gradient descent from before. So you still have an outer loop that runs until convergence, and we still got these updates in here. But before, we calculated the error for all the examples, potentially millions of examples. So calculating this here was super slow, and it converges, but it takes super long. And with our stochastic gradient descent, I would just calculate the error on one example. So I go through all my m examples. I calculate the update for one example. And I do this then for the next example, and then in the outer loop, I just finish once there's a convergence. Do you think I get a proper result if I calculate the error only for one example rather than all examples? If you think this leads to the correct error, thumbs up. If you think it doesn't lead to the correct error, thumbs down. And maybe some more responses because it's a tie at the moment. So there's a big majority for not. Yes, this does not lead to the correct error. So there are some approaches that mix the two algorithms, a so-called, for example, mini batch gradient descent, or we still call a stochastic gradient descent, that we don't calculate this error for a single example, but for a few examples at the same time. For example, we take 100 or 1,000 examples, not millions. If I take a mini batch, does this lead to the correct error or still potentially to a wrong one? Thumbs up, correct error. Thumbs down, still wrong, potentially wrong. And some more answers. So you all think from the answers that the mini batch would give me the right error. In fact, it does not, because for the right error, I still need all examples, not just the mini batch. I can try to improve it by initially randomly shuffling the whole data set, could help, but even such a mini batch gradient descent will still potentially lead to wrong errors. So you wonder, why have I put it in here? It may lead partially to wrong estimates, but it will lead to better updates very, very quickly. The screen share will be with us in a moment. Just bear with me. I will show you now a new visualization that you have probably not seen before yet. It's a so-called contour plot. Has anyone ever seen a contour plot? So thumbs up if you have never heard about this, thumbs down. I'll show you now what a contour plot is. Um, I can only visualize it well in with two parameters. Imagine I have this statistical model or this neural network, this machine learning model has two parameters, weight one and weight two. And there is a minimum, which is here. And then I put these contours around it. That means the further I go away, I have more of these rings. So it's sort of um, down here is the minimum. It's sort of a valley, and I want to get into this valley. Um, we could visualize in such contour plots, obviously more complex contours where I have multiple minima and kind of stuff. But here we still assume I just have one minimum. And I'm starting now, say up here with red. This is the start, and in blue, it's the goal. And what I want to do is I want to change my weights one and weight two so that I get towards this minimum. With my classic batch gradient descent, so the original gradient descent, I will always get closer to the minimum because I look at all these examples, assuming it's convex, assuming I really only have one minimum. Then there was a question from the terminology. Yes, stochastic gradient descent would typically mean just one example, and mini batch, you can define the batch size. Sometimes people use stochastic gradient descent also as a synonym for mini batch gradient descent, where you use a few examples, but that's the terminology. So this would be the start for the batch gradient descent. So batch gradient descent, meaning really all examples. Now, say I have a start here for my mini batch gradient descent or stochastic gradient descent. I may get towards the minimum, but I may wander around it because I do these updates and sometimes they will just lead me off from getting to the minimum. So sometimes they may take me in the wrong direction, but ultimately I will also make it to the minimum. The thing is, I can calculate these updates much, much quicker because I just look at a few examples, then I do an update. Maybe I get towards the minimum, sometimes a bit off, sometimes in the wrong direction, but I just make a lot of updates in a short amount of time rather than waiting until one big update is calculated. Because with my batch gradient descent, yes, I will get closer to the minimum, but calculating these updates just takes so long. So this mini batch gradient descent or stochastic gradient descent, not all of the updates are correct, but empirically I will get much, much quicker to the minimum, especially when I have a lot of examples. And also if I have a more complex error function, because the error functions we saw here, they are simple. I just have one minimum. In reality, I have a lot of minima, and I want to quickly get to a good minimum and potentially also get out of a bad local minimum, that I don't get stuck in a bad, very high local minimum. Rather, I want to get out and get into a better local minimum. And with a classic batch gradient descent, I will not really get out of the minimum anymore. But with the stochastic gradient descent or mini batch gradient descent, I can oftentimes even get out of such a really bad local minimum and then get to a better one. And all of this goes much, much faster. And that's why such a stochastic gradient descent or batch gradient descent is very much preferred. And this is what also libraries would typically offer to you. There's one last question. How do I actually calculate partial derivatives? I need the partial derivatives, but how do I calculate them? This is something that is overall quite complex, and in the literature, you often find a reference to an algorithm that is called backpropagation. Backpropagation would calculate me these partial derivatives that I would then use in gradient descent or stochastic gradient descent, mini batch gradient descent, whatever. For now on, when I refer to gradient descent, I just refer to this family of gradient descent algorithms. But I need the partial derivatives, and calculating them is difficult in a neural network. In other models, they can maybe be calculated very, very easily, like in a linear regression or logistic regression. Calculating them is very, very easy. But in a neural network, this is quite complex. And for this, there is backpropagation. This is something that would be explained in greater detail in your deep learning class. You will anyway use machine learning libraries, so we don't need to study backpropagation here in detail. We use libraries for neural networks, but just to say what backpropagation does, it is will calculate you these partial derivatives. Sometimes in the literature, gradient descent and backpropagation are mixed up. Sometimes the literature refers to backpropagation, not only calculating partial derivatives, but also doing the gradient descent. But in the literature I prefer, and in my wording, I like to split the optimization algorithm, which is here, for example, gradient descent, split it from the calculation of partial derivatives. And for partial derivatives, we use backpropagation. There are some other approaches as well that we will see later today. But if you hear about backpropagation, all you need to remember is, that's the one to calculate the partial derivatives in some way. Backpropagation works well if we have if we have random weights initially. If I only have all weights zero, it's an approach I take in a lot of machine learning models. But if I do this in neural networks, your training will not go very well, and it could happen that you sort of learn symmetries. It could happen that these units learn the same as the units up here, and this could be in fact recursive. So you have a neural network, but there's not too much learning in it because you learn a lot of symmetries. This can happen when you use backpropagation on all values zero. So you would rather prefer to initialize all weights with small random values, positive or negative, around zero, because then you don't learn these symmetries and you can actually take full advantage of your neural network. That's why oftentimes you would see in the top that we would assign random values initially to these weights. This was now classic neural networks. And next, we will start looking into deep learning. So recent advances in the last 15 years and how we can eventually use them for computer vision. Now we actually look into much bigger neural networks, so-called deep neural networks. I mentioned them briefly when we looked into the history of neural networks. So a deep neural network would still have an input layer and an output layer, but we would have many hidden layers in between, because with these deep neural networks, we can learn features on our own quite well. And this is possible now for the last methodology started some 20 years ago, and it's really been used a lot in the last 10 to 15 years because we have a lot of hidden layers. The challenge is a lot of hidden layers means we have a lot of parameters. And a lot of parameters means oftentimes in machine learning that models tend to overfit, mean they learn the training data pattern very well, but they really don't generalize to new inputs. But the goal of machine learning is to generalize. And with the methods we have available nowadays, we can build large, deep neural networks and reduce the overfitting. And these deep neural networks are so cool because they self-learn features. So I want to visualize this here. This is from a Google experiment some 15 years ago or so. What they wanted was they want to build a neural network that can detect whether there is a human or a cat in an image. If you try to use features on your own, we've seen the challenges. So the best thing is to learn this purely from the data without any feature detectors before. And a deep neural network works very well for this. And then if you try to visualize what the units learn, the first units, they learn on their own simply simple patterns like an edge. Later layers learn groups of edges like faces. Later layers learn groups of groups like whole humans, whole cats. And we don't need feature detectors for this. In most of the deep neural net, actually almost all the hidden layers in the beginning, almost all of them from the beginning, they are there for feature learning. And just the last few layers are there for the actual learning of the task. So to, for example, do the classification. And for computer vision, we can visualize this quite well. If this was audio or text, we couldn't visualize it that well. That's why I also like computer vision examples. And with deep neural nets, there are lots of challenges. For example, how many hidden layers do I need? How many units per layer do I need? Overfitting is a real issue because a lot of parameters typically lead to overfitting. How many training examples do I need? Typically, the more the better, as long as they are representative. But if I have a lot of training examples, training time becomes an issue. So that's something we also need to control. And for this, we'll see solutions today. We had visualized this sigmoid function today. You remember this function, this 1 divided by 1 plus e to the power of minus x, which is visualized here in blue. So it's 0.5 for input 0 and converges to 1 for larger positive inputs, and for larger negative inputs converges towards 0. And this sigmoid function has been popular, or was popular, for decades. And it was noted also some 10 or 15, probably 15 years ago, that the sigmoid function itself also contributes a lot to overfitting. And then some 15 years ago, the so-called ReLU function was proposed. It's in red. It actually looks much simpler because it's 0 for input 0 and negative. And for positive inputs, it's just a linear output. And ReLU stands for rectified linear unit. And this ReLU function as an activation function actually helps a lot to reduce overfitting. And since then, lots of variations of the ReLU function have been proposed for different use cases, and always with the aim of reducing overfitting. And it turns out this ReLU function can also be calculated much easier because it's 0 or just a linear output, much easier than calculating a fraction where we need the exponential function. So we can also do predictions much faster, and therefore we need predictions in the training also for calculating the errors. That means also the training will go a whole lot faster. Plus, there are some more positive effects of the ReLU function. So if you hear about ReLU, this is the rectified linear unit. Now we have still seen a regular deep neural network. And we've always said today, if we have an image, we would just take this 2D image and turn it into one big vector. So we just glue all the rows together and we have one big vector input. This does not work very well for images because you've learned in this course that in images, we have spatial relations, that a pixel is affected by its neighborhood, and not just the neighborhood left and right, but bigger neighborhoods. And that relation gets totally broken if I just turn my 2D image into a big vector. So we need a different type of neural network that can help us to process 2D input. And that's a convolutional neural network. And convolutional neural networks, again, they go back to the 70s, 80s. But now with this deep learning, or in this deep learning era, they have become super popular again because we can also build very deep convolutional neural networks and we can learn super complex features from vision input and then do some task with it. And the convolutional neural network works the following. So I have a 2D input, my 2D image, which so far we had not used. Now we'll use it. And in the convolutional layer, I learn so-called convolutions. And these convolutions, you've seen convolutions before in this course, and we'll apply this concept now to neural networks. So we have a so-called mask, and this mask will look into an area of the input image in blue. And we train many masks in the neural network. So we also have a red mask that looks into here. And we see these masks are overlapping a little bit. And there are some good reasons for that because we want these masks to overlap so they can share some of the pixel information. And this will help us later to become invariant to translations. That means it doesn't matter where the object is in the image, if it's in the center, upper right, lower left, we will still find it with this masked approach where these masks overlap. And convolutional neural networks have some extra complex parts, don't worry. We will see this very soon. And the beauty is when they start overlapping, I become invariant to translations, as well as potentially to some rotations to some degree, because I can customize how they will overlap. And eventually, I will calculate features in this convolutional layer, and I will have a lot of these features spread out the convolutional layer, and they have a lot of information, and I want to compress that information in a so-called subsampling layer. And in the subsampling layer, I will again have this window. I will calculate features from a window in the convolutional layer, but in a subsampling layer, I oftentimes do simpler stuff. For example, a max operator. I just want the maximum value from this window, or the minimum value, or the average value. So this subsampling layer leads to some compression eventually. And we'll study those convolutional neural networks now in greater detail, and they really help us to find or to learn features in an image. And in complex neural networks, I not only have one convolutional layer and one subsampling layer, but rather I combine them. I have a convolutional layer and a subsampling layer. Behind, I have another convolutional layer and another subsampling layer. Sometimes I have multiple convolutional layers together and only a subsampling layer later. And this is an approach to learn very helpful features from vision input. And convolutional neural networks are not only used for vision, they can also be used for text, for example. So this concept can also be applied to text, but we'll focus on the vision part in this course. And the neural networks are now super popular, or neural networks are super popular, so are convolutional neural networks. Transformers, they do something different. We will compare the transformers to this approach here in a couple of weeks. The difference doesn't matter too much yet. And there's a question here if there's the claim that the masks in the convolutional layer then manipulate the original image. So they lose information. Well, you'll see in a moment how they work. Probably it will be easier to answer the question then. But I built a lot of features from different parts of the image. And later I will become invariant to some level of translations and rotations if I do it right. And the subsampling layer compresses information essentially. But we'll see how this can be put into bigger networks very soon. Again, we have seen convolutions many times in this course. There's just another example here, say without normalization, I apply this kernel to this image and I multiply the corresponding values. So a 0 and 0, a 1 and 1, which is 1, and then 3 times 2 plus 4 times 3, this will be add up to 19. I can move the kernel to this one here, I will get 25. I can move the kernel here, and I move the kernel there, and I get these corresponding values. And this principle will be now used in convolutional neural networks. The convolutional neural networks, they are built on 4 important ideas, which are sparse interactions, spatial arrangement, parameter sharing, and equivariant representations. And that you know what these terms mean. We'll now look into these 4 terms, and we see what this means in this architecture. And then we look at some, or not architecture, in this approach, and then we look at some sample neural networks that take advantage of this. So sparse interactions. In a traditional neural network, we have seen we connect all input units to all hidden units in the first hidden layer. Then every unit with every unit in the next layer and so forth. That means every output unit eventually is connected indirectly to every input unit through these hidden layers. This is great, but it can lead to lots of complexity and lots of weights. And with sparse interactions, we try to reduce this. And we will actually do this in order to reduce complexity of the model, because later we want to reduce overfitting, we want to train it quickly. So these sparse interactions are helpful for us to store fewer parameters. We reduce the memory footprint and improve the statistical efficiency of the model. We have less operations and possibly much less overfitting. Because these kernels that we learn now, they only look at small regions of the input image, not at the whole input image. And this is often visualized as something like this. So I have a kernel here that looks, so in the blue convolutional layer, that looks, or that has a receptive field, which is part of the input image. And I have weights to connect the pixels together with the with that unit in here. So I have weights that would allow me to connect the individual pixels, each of them with my feature. And I could even have multiple features here that would all look at the same window, but with different weights. So this would first of all look like we create some redundancy, but in fact, we would train different feature detectors. So we could find different features in that one part of the image. And that's why I have multiple of those feature detectors stacked here that all have the same receptive field, but different weights. So I would find different features for further processing. But it makes sense that these feature detectors don't look at the whole image, and that's what sparse interactions mean. If I looked at the whole image, I would ultimately have super complex feature detectors that become super slow, and I wouldn't be able to afford a lot of them. So I rather address local features, not global features. And that's why I have this receptive field. And this can also be visualized the following. So if I have down here, this would be a classic neural network approach. Imagine I have a feature X, and the feature X would look at, it's explained down here. And well, now the features are this one here. So I have X is the input. X is the input in a classic neural network, which was this vector of inputs. So for now, we just look at the vector. Later, we will see this in 2D. And I have features here, which are S1 through S5. And we would see this input X3 would affect all the features in a classic neural network, as we have seen it in a fully connected neural network. But when we have these sparse interactions, we would see that this input X3 would only affect S2 to S4. And therefore, the receptive field, say from a vision perspective of S4, would be X2 to X4, because those influence S3, but not all of the inputs. So this is how I could visualize this receptive field and these sparse interactions. But I can stack these sparse interactions, so I can have multiple convolutional layers. I have my input x1, and I can have multiple of these layers. So this would be the first convolutional layer. Then I have another convolutional layer. So I would stack them, and I would build increasingly more complex features, so that eventually, when I stack it, that my G3 feature would have a receptive field to look at H2 to H4, but H2 looks at X1 through X3, H3 at X2 to X4, and H4 to X3 to X5. So if I stack like this, I can still have a very big receptive field when I stack, but I need much less parameters than in the original setting, especially assuming I have a lot of inputs and not just 5 of them. So this stacked approach certainly helps to keep the number of interactions sparse, and therefore we need less memory and we will generalize better. We also need to think about spatial arrangement. So there's a lot of text here, but the text is also, if you want to get a second explanation or for your revision, when I have my kernel that, so it has its receptive field and it looks at a part of an image, I can move it around. There are lots of things I can think about how I can move it around. How do I treat this corner? And there's a 0 and there's a corner. What's actually around the corner? I could assume it's all zeros. So eventually I would not start looking at this window, but actually at this one. So I'm highlighting it here. So this would allow me to also pay more attention to the corners and the edges of the image by putting some zeros around it. This is something we call padding. Then we also have the question of how I can move this kernel around. Can I just move it around from by 1 pixel to the right, 1 pixel down, or can I move it, for example, by 3 pixels in the height, 2 pixels in the width? So for example, if this was the first window I'm looking at, I could move it by the height of 3 and the width of 2 to here, and not just 1, 1. Because if I move it by 1, 1, I will create a lot of features. If I move it by more, I would potentially have less features, but maybe they don't overlap anymore. So you wonder, how do I set these hyperparameters? For this, unfortunately, it's a lot of trial and error, or you use some best practices shared by others, because you want to get much information out of this, but you also don't want to create too many features, because if you create too many features, you tend to overfit. So it's a little bit of trial and error, but there are lots of best practices that we will see. There's something explained here in the slide, which I took from this Goodfellow deep learning book. I'm not explaining this here in detail, but if you want to study the spatial arrangement in greater detail, feel free to look at this slide. Now, if I go back to the to this image here, imagine I have this feature that looks at this area. I could have another feature here which looks at that area, and another feature looking at that area. That can be done, but I create a lot of features that have nothing in common, but actually they are all I'm looking for that object throughout the whole image. And I create a lot of feature detectors, and that can be helpful, but if I create a lot of them, I add a lot of complexity. And maybe I want to create feature detectors that share some of their parameters. That means when I start looking for some object or some features, I train that one feature detector, and I not only apply it to one part of the image, but I apply it to multiple parts of the image. So some of the features would share the weights, And like this, I reduce the overall number of weights. And I would also make the learning more robust. Obviously, I will have multiple features, but some features will share some of that information. So when we look at this one here, this feature with weight sharing could be applied to other regions as well with its weights, but this feature could be applied also to this region as well as other ones, but that feature has other parameters. This is better than training a whole new set of features that is completely different than just for this region, because this would add lots of weights, lead to overfitting, and maybe less robustness. And that's what parameter sharing aims at. And this is explained here with some visualization as well, but what I said so far is we do parameter sharing and would help us a lot eventually to build more robust features and have less overfitting. There's another concept that is called equivariance. This is also reflected in a neural network. And equivariance means if the input changes, the output would change the same way. And when I use the concept of equivariance, this can help me to build more robust convolutions. And for example, when a convolution creates such a 2D map where certain features appear in the input, if we move that object in the input, then the representation will also move the same amount in the input. And that concept is helpful. We'll come back to these concepts later and see how they work in practice. These four concepts that we've just seen, they're in the convolutional layer. And behind a convolutional layer, we've seen before, we could put a subsampling layer. Sometimes this subsampling layer is also called a pooling layer. And what it does is it calculates a summary statistics of the convolutional layer. For example, this can help us, or we calculate the maximum, the average, weighted average, or minimum. So from that window where that feature in the subsampling layer looks at in the convolutional layer. And this helps us to become invariant to translations in the input. It reduces the overall complexity. We do some compression of information. And this is helpful to become ultimately invariant. So it's a combination of convolutions and poolings that we would do. So what does that mean in practice? I have a very good example image here that shows us what all of this is about. Imagine I have this input image and I want to classify it into, for example, a robot, or into a robot is broken or not, whatever. I would calculate a lot of features through my convolutional layer. They would look, for example, we have one feature here in the convolutional layer that would look into this part of the image. And I try to find different features. Could be a hand, could be other stuff. I don't describe the features, but I rather learn features that make statistically sense. And then in this convolutional layer, we have all these things like weight sharing. We calibrate how to move the window around, 1, 1 or 2, 2, how much should they overlap, whatever. And we have a lot of features in here then, and we compress them with the subsampling or pooling layer. We could say, well, this is enough. We now have useful features. And finally, we need to do something with those features. So I've just skipped this part here, but I'll come to this in a moment. But I've calculated or I've learned features on my own, and these features will be used now in a few hidden layers of classic units to learn the actual task. For example, classification, regression, or something different. And for this fully connected layer, or I would have a fully connected layer here, typically maybe 2 or 3 fully connected layers to learn the task. But before I learn the convolutions and do the subsampling. And sometimes I need to combine this with another pair of convolutions and subsamplings. Sometimes just a few convolutional layers and then some subsampling. And later we will see very complex neural networks that have a lot of hidden layers, sometimes hundreds of hidden layers, but most of those layers are just for convolutions and subsampling. Only the last, for example, two or three hidden layers are for the actual learning of the task, and then I have the output layer. But most of the layers are for the feature learning, and then I do something with the features. Because just classifying features into something, two or three hidden layers is enough. So most of the layers I would need is actually for learning features. The good thing with this approach is I don't need to choose a feature detector, but rather I learn features that make statistically sense. And and that's certainly a helpful approach. The problem is I need a lot of data, I need a lot of computing time. If I have a simple feature detector, like we've seen last week, some of them, and I apply them first, yes, that's probably much cheaper. And I would use those features and then two or three hidden layers in here. But which feature detector do I use? Is it invariant to whatever or not? And the neural network is obviously not perfectly invariant to every kind of noise. They are not. Well, these convolutional neural networks are particularly made for translation and a bit of rotation, but I don't need to do trial and error when picking my feature detectors, but rather I learn features that make statistically sense. These convolutions, so there's a question here. If I could illustrate the forward flow in this diagram, um, the feature maps, they first extract features. Initially, yes, very, very simple ones, like just edges or corners. Then we would do some compression on these features. And from the compression, we would learn new features and compress again. And what happens in here is in this flow, we would learn increasingly more complex features. So the first few layers, they would first learn very simple features in vision, like edges, for example, corners and this kind of stuff. And the later convolutional layers, they would learn more complex stuff, like, for example, groups of edges, groups of groups. We had a sample image here that I talked about, which was something like this. The first few layers would learn simple stuff, later layers, more complex stuff. That's the idea of the the convolutional neural network. And there's a question if each feature map is for each type of feature. Well, we don't define the types of features. I mean, they are, it doesn't mean that this necessarily only detects edges. It detects the features that make statistically sense. We don't say, we don't give the task, we don't say you have to find edges. It could be something totally different than edges, maybe some other strange structure which makes sense from that data and that is statistically useful. So we don't force this to learn a certain feature, and the one here could find some edge, the other one maybe some corner or some other type of edge. And they're not just that one kind of edge. These edges could appear in different size, in different shape, and eventually, and it's just small edges initially, and then maybe larger groups of edges in the later layers. But this kind of stuff can be visualized, and there's a very good GitHub or explanation on GitHub that you can try out and read on your own during the Easter holidays in case you wish, which is from a Stanford course that also provides some insights of how you can visualize units in a neural network and you can actually visualize what they show. So for example, some feature looks like this. This was for a colored image and not just a grayscale image. And maybe this kind of feature seems to appear often in the image. And you can try to visualize it. And I can also quickly open this. Just wait a second. We'll be ready in a moment. So this is from the Deep Learning for Computer Vision class from Stanford, and it explains how you can visualize weights, how you can visualize these features, and it refers to some other papers that have shown this, and it has some further references. So feel free to read this in case you want to learn in detail how to visualize the units. Few groups had done such kind of work also as a project in the past. This doesn't mean that I'm recommending that everyone would do such a project in this course, but it's something that I've seen before also as group projects could be a hint here. Now, we'll come back to a few more questions of how we can actually train a neural network efficiently. And then we'll see some best practices and some sample architectures that have proven to be helpful in recent years. What we need are the partial derivatives in a neural network. And we've talked about backpropagation, but eventually it's not that easy. Because when I do backpropagation, I need to know what's the structure of the neural network. And I can change the structure of the neural network. For example, I add more hidden layers, I change the size of the hidden layers. I can change the loss function. I could change from squared errors to cross entropy or some other loss function. And I need to change the code of my backpropagation ultimately to reflect that structure or the change of structure. I could also come up with some new rules and say maybe not every unit is connected to every unit in the next layer, but only to some of them. And for that, I need to update my backpropagation as well. So, and in this course, we want to use many different neural network architectures, not just that one kind of architecture and hand it out to everyone and use it. I want you to come up with your own neural network and change its structure. That's what people are doing nowadays. And that's something that was quite tricky until maybe 15 or 20 years ago. Because if you change the architecture of your neural network or some of the rules in it or the loss function, you could not just run backpropagation again on it, but you had to change your backpropagation implementation to reflect that new structure. Only then you would be able to have the partial derivatives, and the partial derivatives are needed in our gradient descent. And there's one extra thing I wanted to say. One student, I hope he or she is still here, referred to the Newton method before. Is that person still here? Probably. If you're still here, maybe just say hi or or send a thumbs up. The Newton method, so they're still here. So the Newton method is originally made for finding the root of a function, so where a function is zero. It can be tweaked so that you can use a Newton method to find the minimum or maximum of a function. And for that, so you can use the Newton method to find a minimum for our weights. And the Newton method also needs the partial derivatives. So the Newton method is eventually a different optimization algorithm. We've seen gradient descent and its variations, stochastic gradient descent. The Newton method is just a different optimization algorithm if you use it right. In some machine learning classes, sometimes some more advanced ones, you would see different optimization algorithms, not just the gradient descent. One that is now very popular for neural networks is called ADAM, A-D-A-M. Maybe I'll talk about it later for a little bit. The Newton one is not that popular for neural networks. It's used for probably a different class of machine learning algorithms. But the good thing is these optimization algorithms, they're highly generic, and what we need are the partial derivatives. And for a lot of machine learning models, we can calculate the partial derivatives very, very easily. but for neural networks, this is more challenging. And in the past, the thing was really you came up with a new architecture, you had to come up with the rules for your backpropagation to calculate eventually all of this efficiently. But you want to change the architecture all the time, so we need something smarter. So how can I compute the partial derivatives? The thing we would really have to do in the past was we need to come up with an analytical solution. So we would need to look into the structure of our neural network and try on a piece of paper to derive these partial derivatives and then implement them in an algorithm, in a backpropagation like style, so that we can calculate the partial derivatives very easy. But if you change the architecture of a neural network, you don't really each time want to sit there with a piece of paper and come up with the analytical solution. If you want to do this, maybe thumbs up. If you don't want to do this, thumbs down. I want to see if anyone actually wants to do this, but it could take weeks or months to come up with these analytical solutions, especially for a very complex neural network. So when I studied machine learning in my master's, we used some literature where you had to come up with these partial derivatives on your own from the architecture of the neural network, and the professor quizzed us on this kind of stuff in the exam for small ones, but it was quite messy. The challenge is this is very time consuming. Probably it's very error prone too, and it needs to be redone for any changes to the network architecture. We want to innovate, try a lot of different networks, test them, break them. So probably that's not the right approach. Yet, if we have them, the execution is quite efficient and we get accurate results of the partial derivatives. And when you looked into publications from 20, 30 years ago about neural networks, so papers, a lot of papers focused a lot also not just on new architectures, but also explained how they derived these analytical solutions of how to calculate the partial derivatives. Very boring, very slow, very challenging. So one of my classes in my master's was largely about that stuff, and we had to know all of this for an exam. And I remember when I interviewed for professorships 7 years ago. So I started in Deggendorf a bit more than 6 years ago, and I applied at a few universities 6.5 or 7 years ago. When you get invited for an interview, you need to give two presentations. One is about a lecture, the topic is defined, and you need to present for 20 or 30 minutes. And the other one is a topic of your choice. So what you are really good in. And there was another university that interviewed me too. And the task was for 30 minutes to explain backpropagation, how to do these partial derivatives on your own. And I picked a very small neural network, I think a neural net. So it was up to me what I present exactly about backpropagation and how to train neural networks. And I picked a very small neural network on my own that had like 3 weights. And then for 30 minutes, I showed in my sample lecture of how that would be done. And it turned out none of the professors who sat in there, because the sample lecture in the interview will be attended by other professors. Maybe you have as students also sat in something like this, because students would also get invited for such interviews that they see how the applicant would teach. And it turned out that the professors at the other university, none of them really understood backpropagation. And I gave my 30-minute sample lecture, but none of them had ever done anything like this before, and they were all largely confused. That was sort of strange. So I wondered, why did they ask me to give such a presentation if none of them had really understood it? They were happy with my sample lecture, but they were all sort of confused. And I said, well, it's a tough topic. I don't know what you expected for 30 minutes. So even a lot of professors struggle a lot with this one here. I learned this very well in my master's, but I'm glad I don't need to do this anymore. There are other things you could do. We could use symbolic differentiation. So we could use a computer algebra system, something like, for example, Maple. Maple or Mathematica. They are symbolic systems, computer algebra systems. And I could give the computer algebra system the structure of my neural network and ask it to come up with an analytical solution on its own. The advantage is you get also very accurate results and there's no manual work, but it's super inefficient. So even computer algebra systems probably struggle with this. And this doesn't scale to very sophisticated functions. I mean, humans don't scale to this either. But either way, if you have a big neural network that is very complex in structure, probably none of these approaches work. Humans don't scale, and computer algebra systems don't scale very well to that either. Computer algebra systems have been available for many decades, but they couldn't really address that issue here too much either. What we could do is we could do a numerical differentiation. Who of you still remembers numerical differentiation? Say from high school or your first year at university, where you, before you started learning how to calculate the derivative of a function, you learned how to do numerical differentiation. One person remembers. Is there anyone else who remembers this? Because we can always say, I have a function. Now we just see this a bit simpler. Ignore the chase. So we have, and the I, imagine we just have an x, f of x, and we add h on top of x. We subtract f of x and divide this by h, and we have a limit where h goes towards 0. This would give us, or that's eventually the definition of a derivative, and we could implement this and calculate the derivative numerically. We can do this for partial derivatives as well, so xj, and we would have to do this for every output unit of the neural network. So we have multiple output units, not just one. That's why fi is the output unit. And we could calculate the numerical or a numerical approximation of the value that we would get from the derivative. So we would plug in a very small value for h, and we would eventually calculate this or approximate it without knowing what the structure of the neural network really looks like. Or we need to know the structure, obviously, but we don't do an analytical solution or symbolic solution, but rather we calculate this for a small value of h. And we have, for one input value, we would finally have an approximation of the we would have an approximation of the derivative. And we can do this for partial derivatives and for multiple output units. So it can be done, but the advantage is simple computations. We don't need to know much math, but we'll get actually super inaccurate results. The choice of h is challenging. And potentially this becomes super, super slow when I have a big neural network with a lot of hidden layers, a lot of output units. This becomes super slow, and I need to recompute these partial derivatives often in my gradient descent. So doesn't work very well, to be honest. The results may not be numerically stable. This approach is sometimes used if you implement something like backpropagation on your own. So you come up with the analytical solution, you implement backpropagation for this. Sometimes you can do a numerical differentiation sort of as a test to see if the solution in your backpropagation actually makes sense, or maybe you had an error in your analytical derivation or in the computation. So this can be sometimes used for testing, but it's too slow to be used in practice. So none of these solutions looks really great. And this is what really, I think, prevented a lot of innovation around neural networks in the past. And there is something available nowadays that helps us a lot. It's called automatic differentiation. Very importantly, automatic differentiation is not numerical differentiation, but it does something different. So automatic differentiation is actually something that's available for longer, but it's been applied to neural networks now in the last few decades. And it refers to a set of techniques that would allow us to numerically evaluate the derivative of a function that we specify in a computer program. And modern libraries implement automatic differentiation. And this is super helpful when we have custom neural networks architectures that for which we don't want to manually compute the partial derivative. And this automatic differentiation, we would use this to approximate the value of the partial derivative by reflecting the structure. So there are different approaches here, as you can see. We have our function, and with automatic differentiation, I get a way to evaluate the partial derivative, and I don't need to come up with the analytical solution on my own. Automatic differentiation, again, is something that would be discussed in great detail in a neural networks class or maybe in a symbolic programming lecture. In this course, we will simply use modern machine learning libraries that embed automatic differentiation. If you want to learn more about it, wait for your deep learning class or for some other, or read some books about neural networks. We'll simply just use it because this is not a deep learning class, so I'm unable to spend the whole term on deep learning, but rather we use libraries, and automatic differentiation is helpful to address these challenges of getting the partial derivatives for any kind of neural network we want. And we don't need to do the analytical solution, we don't need to do symbolic differentiation, and we don't need to do numerical differentiation, but automatic differentiation will address this for us. Now, there are lots of deep learning libraries, frameworks for us. TensorFlow and Keras have been combined. They're very helpful. So TensorFlow came originally from Google, that they built their own deep learning architecture, made it publicly available. PyTorch is a different approach. There are other libraries as well. In the past, there was one that was called Lasagne that was very popular in the early days when deep learning came up. With Lasagne, the idea is you have different layers and you stack them. So Lasagne was popular in the past, but probably is not really big thing anymore. People now focus on Keras, PyTorch, and probably a few other ones. For your projects, if you want to do deep learning, feel free to use these libraries. Don't reinvent the wheel, because, for example, with Keras, you can build your own convolutional neural network quite easy. You would build a model. Sequential here would just mean a regular layer, which would be an input layer. Then you add a convolutional layer with a certain size and so forth, and an activation function. You would do a max pooling next. You would have another convolutional layer, another pooling, another convolutional layer, and so forth. And you can easily customize the size of this. You can customize your activation function. So you don't need to build all of this from scratch. Please use the libraries because they run efficiently, and they will bring you to speed to build something more useful. We've talked about hyperparameters today, and hyperparameters are these global parameters in a model, like, for example, the activation, the learning rate, which was this alpha. But there are other hyperparameters, like the number of layers, the number of units per layer. There's something called a regularization factor as well. And regularization allows us to reduce overfitting in a model. And the problem is, how do I do model selection? How do I find the right number of layers? How do I find the right number of units per layer? How do I find the right number of, or the right value for the learning rate? There are lots of approaches. One approach could be trial and error. So you would randomly try a number of layers and hope it works. You could use something that is called grid search, and grid search would mean you define possible values for the number of layers, for the number of units per layer, and then you would try combinations of that. You would, for example, try 5 hidden layers with 1,000 units per hidden layer. You could try 10 hidden layers with 500 units per hidden layer, stuff like this. So in a grid search, you would try all of these combinations, but oftentimes you not only have two hyperparameters, but many hyperparameters. So the grid search becomes super inefficient because what you have is the curse of dimensionality. You simply have a lot of possible combinations that you're unable to try because for each of these combinations, you need to retrain the whole model. And training is super slow as well, potentially. So grid search doesn't work too well, and you need to define the possible values. So 10 hidden layers, 5 hidden layers, maybe 7 is the right solution. We don't know. So there are better approaches like randomized grid search. You would just define the intervals and the type of the variable, for example, integer, float, and the intervals. Then it's still a grid search, but it doesn't try all the combinations. It rather samples from from these intervals, and it will try, for example, 7 hidden layers with a learning rate of 0.0528, which comes from this interval. And something like a randomized grid search would often help that you maybe have a few dozens of attempts, and for each of them train the model and quickly get an okay solution. Not the best solution, but probably an okay one. And that's something that is used in practice. And there are still better approaches. And the better one is, for example, AutoML, automated machine learning. So what is AutoML? There's a question here if we can do gradient descent again for this. Yes, we want to do some sort of optimization of this. And AutoML doesn't use gradient descent, it does something slightly different. But imagine I don't just want to do random trial and error or grid search, but I want to do something smarter. And each time I have an attempt and I see how my model performs, I want to learn from that too to get to a better solution. I guess this is what you meant here in the chat, if we could use gradient descent for this problem. And this is where AutoML comes into play. AutoML describes the idea that we automate finding the hyperparameters. You could apply AutoML to more than just finding the hyperparameters. For example, how you pre-process your data. You could also apply AutoML maybe to feature engineering. And it's sort of an automation of how you solve the issue of hyperparameter optimization. And you would also learn each time you have built a model, you would learn from this. And some really good AutoML frameworks, they use internally machine learning as well to optimize the AutoML process. So I guess that's what you refer to in the chat. So we use machine learning to optimize our machine learning problem. And this is something that has become popular in the last 10 to 15 years. And like there is scikit-learn. Scikit-learn is a library for machine learning. There's an AutoSKlearn library. And all I say is I have a classification problem. I want an AutoML scikit-learn classifier. So I don't care about which classifier we use from scikit-learn, if it's a Gaussian process, if it's a random forest or whatever. But the AutoML library will do this for me. I say, well, this is my input data, this is my labels, train a model, and then the AutoML model will, or the AutoML library will try to find me a model that solves my problem using machine learning internally. Often it uses some Bayesian statistics approach for this, not necessarily the gradient descent you propose, but it uses machine learning. And such libraries have become popular This one here, AutoSKLearn, is for scikit-learn. For Keras, which is a neural network library, there's an AutoKeras. And for the other libraries, there are other AutoML variations. And I could say, for example, in AutoKeras, I want to classify images with some neural network. I don't care about what it really looks like. If it uses that many convolutions and that many poolings, typically it would be obviously some convolutional neural network, but the exact architecture, I don't care. Just try out and use machine learning to quickly find me one for my task. You can customize this sometimes a bit more with which trials, if you give any hints or something, and eventually you will get some classifier. You can obviously look into it and study its architecture, and you don't need to come up with this on your own. So a lot of things we've said today can be summarized, in fact, in 3 or 4 lines of code. We need just the import, we need the classifier, we need to train it, and then we use it to predict. So just a few lines of code and it works. It's not that easy, in fact. It was sort of a joke. It doesn't summarize this class because in reality, you need to do a little bit more. You need to understand what you're doing. You maybe take the AutoML result and you still further tweak it. And you still need to know maybe how to pre-process your data and look into your data, if your data is correct, if there are any issues in it. But it certainly helps you to speed up. And but you still need to know the theory because you need to assess if this makes sense eventually and that you can do debugging of your outputs. That's overall very helpful. Obviously, your project would be more than just 4 lines of code, but it can help you in your project maybe to find a good classifier. So you're not only allowed to use such approaches, you should, because in industry, you don't get paid for spending 2 weeks on finding some model that works okay if someone else uses this library and finds maybe in a few hours a model that even works better than yours. So take advantage of this automation. There has been this hope to use AutoML for more, for data pre-processing, for data selection, data quality. Uh, some people believe that we could fully automate this machine learning pipeline. I don't really think so. We can automate certain tasks, but especially when it comes to data quality, assessing data, we still need to have domain expertise, whether the data actually makes sense or not, and talk to domain experts. That's something that can hardly be automated, but for some tasks, these AutoML libraries are helpful. Now, how can I speed up my training? And nowadays, we use a lot of GPUs, and GPUs have become very popular. Um, GPUs have thousands of cores nowadays, and GPUs were originally made for computer graphics tasks, for rendering. And in computer graphics, we typically have a lot of linear algebra operations, such as adding matrices, multiplying matrices. With that, we can describe a lot of computer graphics tasks. And it was noted some 15 years ago that you can use GPUs to speed up the training of your neural network. What happens is the following. We looked before into gradient descent, and I had shown you that we turned eventually we looked at gradient descent from a perspective where the weights are a vector, the gradient is a vector, and we just subtracted eventually vectors, rather than having in the loop a lot of individual statements that we would process. And if you do that, we call this approach vectorization. And vectorization means that we try to get rid of loops as much as possible and individual statements, but rather let our operations be expressed in linear algebra, vectors, matrices. And then this can be executed efficiently on a GPU. How can it be executed? Well, we have to program the GPU. So NVIDIA uses CUDA, competitors use something different. But you need to learn how to write code for a GPU. And that doesn't work too well because you need to write a lot of low-level code. So nowadays, what we have also for the last 15 years or so is super helpful because we can use libraries like TensorFlow or others. We write code in Python and finally it gets compiled automatically into GPU code. Maybe not as efficient as if a GPU expert writes the code, but overall very well. So you don't need to know much about GPUs, but rather you write your code in Python and it gets compiled into code for a GPU. And because this works well and we can do vectorization well nowadays, GPUs have become super popular. We use them for training. They are made for operations on linear algebra structures, and we don't need to code all of this on our own or run it on a CPU. And that's why NVIDIA has become so popular because they fuel this deep learning movement with their hardware. I had the pleasure to meet Jensen Huang last year. I met him personally. So they had a big NVIDIA event last year in Paris, and he gave a speech in front of thousands of people in a big auditorium. But they invited a couple of AI experts from Europe to sit together with him for a 1 hour discussion. And I was very impressed to meet Jensen Huang personally. I also asked some questions and discussed some stuff with him. So he knows a lot about technology, but he's also a very good salesperson. And obviously, he hopes to sell ever more GPUs. But my advice is deep learning and neural networks, they're all very helpful, but they're not a silver bullet. There are still probably most machine learning problems we don't need neural networks. In computer vision, neural networks are helpful probably for the majority of tasks. In general, machine learning probably only for maybe 10 to 20% of our learning problems. And a lot of learning problems can be solved much easier with other methods. And certain computer vision tasks as well. If you have a controlled environment, maybe a template approach is enough. Or some classic machine learning algorithm. Runs much cheaper, you need less data, runs much faster, you don't need a GPU. So don't always just go for deep learning. Deep learning can be the solution probably to more than half of the computer vision problems, be it a convolutional neural network, be it a transformer or whatever. But deep learning is not a silver bullet, and deep learning is not generally better than other approaches. Better for certain problems, but not in general. Jensen Huang is a great salesperson, great marketing guy. So it was interesting to meet him last year in Paris. And I also took a photo with him and had a great discussion. It was certainly an interesting experience. And now we have thousands of cores on a GPU. Why is that so helpful? We'll do the lecture a little bit longer today, but because I just want to finish this efficient training here. A few years ago, someone said to me that CPUs would have no future. In the future, we would only need we would only need GPUs. What do you personally think? Do you agree with the statement? Thumbs up or thumbs down if you disagree. And not only with regards to neural networks in general, and maybe some more responses from your side, please. Yeah, I see no agreement with this statement, and I also don't agree with this. So this statement does not come from Jensen Huang. It comes from someone else that I know personally. Um, but Jensen Huang sometimes creates the impression that you would only need GPUs, but he didn't say that quote, and he doesn't sell it that way. I just want to highlight this. So CPUs and GPUs, they differ a lot. So CPUs, they execute typically simple and complex instructions. Simple ones can be some additions, complex ones can be some other data type, some bigger instruction. And you can program CPUs relatively easy, be it in Python or in C or C++. And CPUs are really good in optimizing really inefficient code. So even if you write bad code, oftentimes a CPU nowadays can speed up bad code for you. For example, with out of order executions, or if you write code in a certain order, like in C or C++, it does not get executed in that order because the CPU uses out of order execution, trying to reshuffle your operations. So you still get the same result, but trying to speed up your computations. A CPU can do branch prediction, meaning it looks ahead into an if and it goes the different directions in the if else and pre-computes them. And once you're actually with your out of order execution at the if else, it will pick the right one. So branch prediction can be done. It's but CPUs are not very good in parallelism. So you have a few cores, you have few pipelines, you have things like SIMD, single instruction, multiple data, so apply the same operation to a whole vector of data, but limited parallelism. I know you have taken like a course in operating systems and an introduction to computer science. Have you ever learned stuff like this? Like how a CPU works and things like branch prediction, out of order execution, cores and pipelines? If you have seen these terms before, maybe thumbs up or thumbs down if you have never come across this before. And would be good. Well, it seems like most of you have not seen this. So it was just a quick summary of how CPUs work. A GPU is pretty much the exact opposite. A GPU has high degree of parallelism, potentially thousands of cores, but these cores only do very simple operations, just adding, multiplying single elements. But this can be used for high parallelism. So you have two matrices, you want to multiply them or add them. You would do this with a GPU because you have a lot of simple instructions on a lot of data. And a CPU doesn't do that very well, but you would rather use a GPU for that. And that's why GPUs are called graphics processing units. So they are made for graphics because in computer graphics, we mainly use linear algebra operations. But programming a GPU is more difficult and they can't really optimize inefficient code very well. So quite the opposite to a CPU. That's why the future does not belong to GPUs. Rather, we need CPUs for certain problems. For other problems, we use GPUs. For training neural networks, we use some kind of GPU. And NVIDIA has come up with a lot of specialized hardware for training neural networks. For example, also tensor units and this kind of stuff. So a tensor is a higher dimensional object, like you have a vector in 1D, you have in 2D a, a matrix, and in 3D you would have a vector, you would have a tensor. So a tensor is a generalization, and there's now special hardware for this kind of stuff. And for example, when in 2015 TensorFlow came out, this library from Google, in which they made their own machine learn or neural network library available to the public, now it's been very much merged with Keras. This helps you even to use multiple GPUs. You don't need to know too much about how GPUs work, but rather you use the GPUs to calculate these gradients, so these partial derivatives. That's most of the computation, calculating partial derivatives and then feeding the partial derivatives back into your main program where you run gradient descent or some other optimization algorithm. Nowadays, we use a lot Adam. So I've written this in the chat, ADAM. Adam works a little bit like gradient descent, but you don't have this global learning rate, but rather you have a learning rate per parameter. So you have multiple learning rates, and you can also update the learning rate on the fly. So this is essentially what Adam does, but all of this is implemented in libraries for you. And there's lots of other hardware that you could use. You could use cloud services. You can use tensor processing units. You can use FPGAs. So FPGAs are field programmable gate arrays, very generic hardware in which you have a lot of flash cells, and you could set this to for a specific computation. For this, you use a hardware description language, and you could describe a hardware that runs on your custom neural network. Some people do this, but I think the majority of people use some kind of GPU, especially the NVIDIA ones. Next week, we will continue with this chapter. And next week, we will look at a couple of selected architectures. So best practice neural networks that others have proposed. Because if we did this now, we maybe needed another 20 or 30 minutes, but we've reached the end. So I want to spare you this, and I want to give you enough time for revision. Then we will look at selected architectures, so best practice neural networks that are available as pre-trained models, so you can use them and apply them to your own problems if you wish. And for this, a revision would be good so that you all remember next week neural networks, convolutions, poolings, and all of that. And be punctual next week at 2 because we'll start with the Cronus challenge. And the Cronus challenge introduction may not be recorded. And everyone is supposed to attend live next week's session. So we also show good attendance to our industrial partners. I wish you a great Easter holiday, and also think about your projects, the Cronus Challenge or your own project, whatever. And if you got any questions until next week, send me an email. Other than that, enjoy the holidays, take care, and goodbye.